Hello and welcome to 3.4, the chain rule. Suppose you ask to differentiate the function f of x equals the square root of x squared plus 1. Okay, so if we're trying to find the derivative of this function, we cannot rely on our previous rules. Okay, notice that this is what we would call a composite function. Okay, it's a combination of a square root function along with a polynomial. Okay, square root function with x squared plus 1. Okay, so we can look at this as if it's the polynomial function embedded within the square root function. Okay, f of g of x. Okay, and sometimes we use the composite notation f of g. So in this section, we're going to be looking at how to find derivatives of these types of functions. Okay, important thing to note is what we'll do is we'll generally find the outer derivative first, and then we work our way inside the function. Okay, so if we have f of g of x, we'll take f prime, okay, and keep the g of x in there, and then we multiply by the derivative of the inner function. Okay, it equates to this statement we have, dy dx will be equal to dy du, and then times du dx. Okay, and picture u it being the inner function g of x. So we find dy du and then du dx, and then as a result du's would cancel and we'll be left with dy dx. Okay, so let's see how this works in practice. So here we have our function. Okay, we'll start off by rewriting f of x as x squared plus 1 to the 1/2 power. Yeah, so just rewriting the square root piece like it's a 1/2 power. Okay, and now to get our derivative, we would do the outer function first, so it's a power rule. So we multiply 1/2 times x squared plus 1, and then reduce the power by 1. Okay, so it becomes to the negative 1/2 power. And then we multiply by the derivative of what we call the base. I like to call the inside the base. Okay, so it's the base being raised to a power. So the derivative of the base would be, well, the derivative of x squared is 2x, and the derivative of a constant is 0. Okay, so this is what it would be initially. And then we try to clean it up a little bit, make it look like one fraction if possible. If we have powers, sometimes we move the negative powers to a denominator. Okay, things like that. And so what ends up happening here is if we multiply the 1/2 times the 2, those would cancel. Right, so the 1/2 times the 2 would cancel. We'll be left with an x on top. Okay, and then the x squared plus 1 to the negative 1/2, that'll go to the denominator as x squared plus 1 to the positive 1/2. Okay, and then we could just rewrite that as a square root for the bottom. So we would get x over the square root of x squared plus 1. Okay, so that's how that works in general. Okay, so we start with the outside and then we go inside. Okay, if we had, for example, y equals sine of u, where u is a differentiable function of x. Okay, first we would take the derivative of sine, which is cosine. Okay, so cosine of that same u, and then we multiply by the derivative of u with respect to x. Okay, so then we could say that derivative of sine u is equal to cosine u times du dx. Okay, so let's take a look at these two examples. Okay, two separate problems. One is sine of x squared, and then the second one is sine squared of x. Okay, so let's start with the first one. So y equals sine of x squared. Okay, so to take the derivative of this, derivative of the sine would be the cosine of x squared. Okay, and then what we're going to do is multiply by the derivative of the base. Okay, so derivative of x squared would be 2x. Okay, and then to just clean it up a little bit, we would typically put the 2x in front so that we don't confuse it with the x squared as being part of the argument of the base. So we put the 2x in front, so it would be 2x times cosine of x squared. Okay, let's take a look at the second part to this. For this second part, we could rewrite this as saying this is sine squared of x. In other words, this would be the same as the sine of x squared. Okay, so if we take the derivative of this, so we have the outer function is the squaring function first. So we will do 2 times sine x, reduce the power by 1, and then times the derivative of the base. Derivative of sine would be cosine. And so now we could just rewrite this without the parentheses, and this would be 2 times sine x times cosine x. Okay. In general, the power rule combined with the chain rule, okay, would be like this. Okay, so we are taking the derivative of some function raised to the nth power. Okay, we do the power rule. So bring the n in front, multiply by n in front, reduce the power of n by 1, and then multiply by the derivative with respect to x of u. Okay, so bring the n in front, and then reduce the power by 1. So let's take a look at an example of how that works. Okay, differentiating y equals the quantity x cubed minus 1 raised to the 100th power. Okay, so outer function first, so the 100 would multiply in front. 100 times x cubed minus 1, reduce the power by 1, and now multiply by the derivative of the base. Okay, so the inside, the derivative there would be, derivative of x cubed is 3x squared, and then derivative of 1 is 0. Okay, and then to simplify a little bit, we have 100 and then times 3, and we could bring the x squared to the front. So 100 times 3 would be 300. Bring the x squared in front. So 300x squared times x cubed minus 1 to the 99th power. And that would be it. Okay, let's take a look at another one. So here we have 1 over the cube root of x squared plus x plus 1. Let's rewrite that. Okay, so we're going to rewrite it. It'll be x squared plus x plus 1 raised to the negative 1/3 power. Okay, and so now it becomes a power rule with the chain rule. So now multiply by negative 1/3 in front. So negative 1/3 times x squared plus x plus 1. Subtract 1 from the negative 1/3. So subtract 3/3. That would make it negative 4/3. And now multiply by the derivative of the base. Okay, so derivative of x squared is 2x. Derivative of x is 1. Derivative of 1 is 0. Okay, let's clean it up a little bit. So we have this quantity to the negative 4/3. That'll go to the denominator. The 2x plus 1 will stay in the numerator. And then the 3 will appear in the denominator for the negative 1/3. So we have negative, this will be 2x plus 1 in the numerator. And then the denominator will have x squared plus x plus 1 to the 4/3. Okay, and that would be it. Let's take a look at our next one. Find the derivative of the function. Okay, so now we have, outer function is to the 9th power, inner function is a rational function. Okay, so again, we start with the outer function. So g prime so we start with the outer function. Okay, so it'll be 9 times t minus 2 over 2t plus 1, reduce the power by 1, and now times the derivative of the inside. Okay, so now inside turns out to be a quotient rule. Okay, so take the derivative of the inside as if it's just a regular quotient rule. Okay, so we would do bottom 2t plus 1 times the derivative of the top. Derivative of the top is 1 minus top times derivative of the bottom. Derivative of the bottom is 2 all over the bottom squared. Okay, so we'll simplify this. So for the top, you're going to distribute the 2 into the parentheses. You'll have 2t, the 1 into the parentheses, I should say. So that's 2t plus 1. And then distribute the 2 in along with the minus. So that'll be 2t. So it'll be a minus 2t. And then that'll be negative 4. And then times negative, that's plus 4. All over 2t plus 1 squared. Okay, combine like terms in that numerator. You have 2t and minus 2t, so those are gone. You have a 1 and a 4. So we're left with a 5 over 2t plus 1 squared. Okay, and now let's look what we could do. So we have this 5 here that we could pull that out in front and multiply with the 9. Now the 2t plus 1, and then this is a 2t plus 1 squared. Okay, we combine those. Okay, same base. Okay, when it's the same base, you have 2t plus 1 to the first, think it, and then 2t plus 1 to the second. Product rule tells us we could make that 2t plus 1 to the third. Okay, so now 5, remember, multiply with the 9, so we get 45, and then we'll have t minus 2 on top, and then 2t plus 1 quantity cubed for the bottom. And that'll be as far as we go for that problem. Okay, using the product rule and the chain rule. Okay, so here we have a product of two composite functions. Okay, so we would use the product rule along with the chain rule. Okay, so first we'll do product rule. So remember, it's first function times derivative of the second function. Now keep track of everything because it'll get a little complicated. So first function, the way it is. Now, as we take the derivative of the second function, you're going to do chain rule. Okay, so take the derivative of this piece. So that'll be 4 times x cubed minus x plus 1 to the third times the derivative of the base. Okay, so times the derivative of the inside, which will be 3x squared minus 1. Okay, plus, I'm going to continue below it. So that was first function times derivative of the second, plus second function times the derivative of the first. Okay, now derivative of the first piece will be times 5, 2x plus 1 reduced to power, times the derivative of the base. Derivative of a 2x would be 2. And then what we do here is to make this a little simpler, we factor out a common factor from both beginning piece and ending piece. Okay, or say first half and second half. Okay, so a common factor. Okay, we notice both first half and second half have a 2x plus 1. Okay, they'll have a 2x plus 1. The common factor will be to the fourth. Okay, so we'll factor that out. 2x plus 1 to the fourth. Next, they also have a common factor of x cubed minus x plus 1. Okay, the common factor would be to the third. Okay, so we can factor that out. So we'll have x cubed minus x plus 1 to the third. And then numerically, they both have, well, this has a 4, this has a 2. So we could factor out a 2. Okay, so we'll factor out a 2. And so what are we left with? Let's see. If we factor those out, that means in the beginning one we'll be left with a 2x plus 1. Let's do it like this. A 2. So 2x plus 1. This came out already. Times 3x squared minus 1 plus, and then from this one we'll be left with 5. I'll put that down here. 5 x cubed minus x plus 1. Okay, this came out and this came out. Okay, so I could have put that maybe in here. Let's try 5x cubed minus x plus 1. Okay, so we're going to look to simplify that bracket. Okay, this will be a FOIL between these two. We'll distribute the 5, we'll distribute the 2 into the FOIL afterwards. Okay, and we'll try to simplify as much as possible. Okay, so the outside here, the 2 will come in front. 2x plus 1 to the 4th, x cubed minus x plus 1 cubed. Okay, let's do a FOIL over here. We'll keep the 2 there for now. So that'll be 2x times 3x squared will be 6x cubed minus 2x plus 3x squared minus 1 plus, and then distribute the 5, 5x cubed minus 5x plus 5. Copy this down, 2x plus 1 to the 4th, x cubed minus x plus 1 cubed. Distribute the 2 into this quantity. So we have 12x cubed minus 4x plus 6x squared minus 2 plus 5x cubed minus 5x plus 5. Okay, copy this down again. Okay, combine like terms. We have 12x cubed plus 5x cubed, that's 17x cubed. X squared would be next, plus 6x squared. Minus 4x and a minus 5x would be a minus 9x. And a minus 2 and a plus 5 would be a plus 3. Okay, in fact, we could now write it without the brackets. It'll just be with the parentheses. Okay, and then this will be the final answer. Okay, differentiate y equals e to the sine x. Okay, so when we have our exponential functions, now remember, e to the something is, the derivative is e to that same thing, so we would have e to the sine x, and then what we do is we take the derivative of our exponent. Okay, so derivative of sine x would be cosine x. Okay, so in other words, when we have y equals e to the u, where u is a differentiable function, y prime will be e to the u times du dx. Okay, and then we could just rewrite this and put the cosine x in front. So cosine x times e to the sine x. Okay, let's take a look at another one. If f of x equals sine of cosine of tangent of x, let's find f prime of x. So that means we'll start with the outside function first. So derivative of sine of something will be cosine of that same thing. Okay, so cosine of tangent x. Okay, and now we have to multiply by the derivative of the inside. Okay, so now let's take the derivative of cosine of tangent. Okay, now derivative of cosine of something, derivative of cosine is negative sine. Okay, so derivative of cosine of tangent would be negative sine of tangent. And then now that we took the derivative of cosine to get negative sine, we have to multiply by the derivative of its argument, right? The derivative of the base. So derivative of tangent would be secant squared. Okay, so the next thing we would do, we would bring this negative out in front like a coefficient, so negative, and then we would have cosine of tangent times sine of tangent times secant squared. Of x. Okay, let's take a look at the next one. Differentiate y equals e to the secant of 3 theta. Okay, so derivative of e to the secant of 3 theta would be e to the secant of 3 theta. And now let's multiply by the derivative of secant of 3 theta. Okay, so derivative of secant would be secant tangent. So secant 3 theta tangent 3 theta. And then multiply by the derivative of 3 theta. Okay, derivative of 3 theta would be 3. Just like pretend like theta is like x. Right, so derivative of 3x would be 3. And then to clean it up, we would put the 3 in front. So this would be 3 times e to the secant of 3 theta times secant of 3 theta tangent of 3 theta. And that would be it. Tangents to parametric curves. Okay, so we have this topic called parametric curves. You'll learn more about it in Calc 2 when we get there. Basically, you have x component and a y component of a curve. They're called parametric equations. And these are curves that are functions. Okay, the x and the y, they're both components of time, of t. Okay, so you'll see an f of t and a g of t. And the way we come across finding the derivative of these functions is we take the derivative separately. Right? So let's take a look at their definition for a derivative. Okay, so dy dx will be equal to the dy dt component divided by dx dt. Okay, and as long as dx dt is not equal to 0, that is defined as our derivative. And doing this allows us to figure out equations of tangent lines to these curves. Okay, so let's figure that out. Let's figure out what's dy dt and what's dx dt, and then we could plug it into this equation. Okay, so let's do dy dt first. So the derivative of 2 sine t would be 2 cosine of t. And then let's do dx dt. The derivative of x would be, derivative of 2 sine would be 2 cosine of 2t times the derivative of 2t, right? The derivative of the base would be 2. Okay, so this gives us, the 2 would multiply in front, 4 cosine of 2t. And so now to get our derivative, we would take dy dt and put it over dx dt. so dy dx equals dy dt over dx dt. Okay, which gives us 4 cosine of 2t over 2 cosine of t. I should correct that while it's still fresh. So we'll do the dy dt. Okay, so let's double check that. Dy dt is 2 cosine t over 4 cosine 2t. Okay, we could reduce between the 2 and the 4. So that gives us cosine t over 2 cosine 2t. Now, one of the things we want to do with this point, we want to convert that to an angle, because that'll help us with plugging into the cosines. Okay, so let's think about square root 3 and 1. Okay, so square root 3 will go out that far, and then to go up 1, say it's this far. Okay, so what would that angle be? This much is square root 3, and this is 1, and we're looking for the angle here. So that would be 1 over square root 3 as a tangent. So tangent of theta would equal 1 over square root 3, which will be square root 3 over 3. Okay, so that means theta is going to be pi over 6. Right, which equates to 30 degrees. Okay, so our theta is going to be pi over 6. So let's do dy dx and we'll evaluate it at pi over 6. So that means we'll have cosine of pi over 6 over 2 times cosine of 2 times pi over 6. Which means we'll have cosine of pi over 6 over 2 times cosine of, that'll be 2 pi over 6, which is pi over 3. Okay, so that means for cosine of pi over 6, that would be square root 3 over 2. Okay, cosine of pi over 3 is 1/2, so this will be 2 times 1/2, which is 1. And so when we evaluate, we end up with square root 3 over 2. Okay, so let's get the equation then. So that's the slope. Now using the point we had in the beginning, square root 3 comma 1 and the slope of square root 3 over 2, we can come up with the equation using our point slope form. Okay, so plug in our values. This is like our x1 and y1. So y minus 1 equals square root 3 over 2 x minus square root 3. Okay, we'll distribute the square root 3 over 2. So y minus 1 equals square root 3 over 2 x minus, now square root 3 times square root 3 would just be 3 over 2. Add 1. And adding 1 to this is like adding 2 halves. Right? 2 halves is the same as 1. So we end up with y equals square root 3 over 2x. Minus 3 plus 2 is a minus 1 half. And that will be the equation of the tangent line. Okay, and that would be the graph of the parametric curve would be the one in red. The graph of our tangent line is the line in blue. Okay, and that's it for today's lesson. Any questions, just email me. Have a great day, great night. We'll see you soon.